quantum mechanical case of an electron transition between two known energy levels. Here we have an electron that we've placed in the n equals 2 energy level. After some time, it will make a transition to the n equals 1 level, emitting a photon. The photon, of course, having the energy equal to the difference in the energies between the two states, and we end up with an electron in the n equals 1 state. Increasing in complexity, we consider the cadmium atom. The cadmium atom is unique in that it has two singlet degenerate states outside of its filled 4d orbital. These two states represent the 5s, 6d, and 5s, 6p states. These correspond to the 1d2 and 1p1 states in the alternate notation. As I mentioned before, these states are degenerate as that they have multiple quantum number states with identical energies. Under the influence of a magnetic field, these states split their energies according to the m quantum number. The 1d2 state splits into the plus and minus 2, plus and minus 1, and 0 states according to the m quantum number. And the 1p1 state splits into the plus and minus 1 and 0 states according to the m quantum number. This splitting of states in a magnetic field is known as the Zeeman effect and is the principal point of inquiry of this report. As with the simple example previously, transitions can be made between these states. However, these transitions must obey the fundamental rules of quantum mechanics. One of these fundamental rules is that delta m is allowed to be either plus or minus 1 or 0. As you can see, groups of 3 transitions will occur based on the delta m of the particular transitions. Here, the -1 delta m transitions are shown. In addition, the 0 and 1 delta m transitions combine to make a total of 9 separate transitions within the split m. Since the groupings of each delta m quantum number transitions all are shifted by the same amount by the Zeeman effect, these transitions will all have the same energy. Therefore, the photons emitted by the 3 sets of 3 transitions will result in 3 distinct wavelengths. Using the difference in these 3 wavelengths with the known energy of each transition, we're able to determine the Bohr magneton using sensitive optical equipment, which will be explained in the apparatus portion of this report.
The optical system used is a Fabry-Perot interferometer, a pair of parallel, highly reflective plates spread a distance t apart. Light incident on the second plate of the interferometer reflects and refracts with the boundaries. The reflected light then reflects upon the first plate and becomes reincident on the second plate. The transmitted light for the two incidences have a path length difference and are allowed to interfere. This interference is evident on the viewing optic as a bullseye pattern due to the cylindrical symmetry of the interference. Consider a single ring of the interference pattern. As the magnetic field increases, the energy of delta m equals 1 and delta m equals minus 1 start to separate. This is observed as a splitting of the ring. As the rings split, you see the delta m equals 0 ring inside, which is unaffected. However, the center ring is unneeded in the analysis, so a polarizing lens will be placed in front to block it out. The goal of the experiment is to determine the Bohr magneton. We do this by measuring the magnetic field of when the two split rings merge. To do this, we measure the magnetic field of when the split rings first touch and of when the split rings